Let's look at this next one. This one's a little bit different. It wants us to calculate the pH at the equivalence point in the titration of 50 mils with 0.1 molar acetic acid. So we have a weak acid, and with 0.1 molar of sodium hydroxide, which we know is a strong base. So I just wrote out acetic acid plus sodium hydroxide, double replacement, right? We're going to get water, right? The H and the OH are going to form water, and then I'm going to have a salt, sodium acetate. So let's write down what we know, that we're given 50 milliliters of 0.1 molar acetic acid. So 50 mLs, 0.1 molar. And we're also told that we have 0.1 molar of NaOH. 0.1 molar of NaOH. So the definition of being at the equivalence point is when my H, concentration of H plus, is equal to the concentration of OH. So we need these two to equal. So let's do a little bit of math here to figure out how many moles we have of my acetic acid. So I'm going to do 0.050 liters times 0.1. So I've got my volume times my molarity to get 0.005 moles. And we need to have 0.005 moles of NaOH. Now, in order to get 0.005 moles, if I know moles and I know concentration, actually, and we can see right here, it's the same concentration. To get the same amount of moles, we would need the same volume. If that wasn't the case, if I had to say 0.005 and I had 0.2 molarity, to find volume, I would need to do moles divided by concentration to find volume. But anyways, so these two are equal to each other. That's great. So this is going to, again, these are my reactants, so I'm going to minus 0.005 to have no limiting reactant, right? Our equivalence point is telling us we have these two equal to one another, so there is no limiting reactant. All right, now we also know that if we're losing reactants, we are gaining products. So plus 0.005 moles of, remember my salt is going to hydrolyze and this is going to split, right? Sodium and acetate. So my acetate then, so I'm going to do a little line here. My acetate, my C2H3O2 minus, added with water. It's going to go through hydrolysis. And what do we get? We get an equilibrium where one of my H's makes this back to its parent of acetic acid, not H2, HC2, H3O2, and that donated one H, so I'm left with hydroxide. Okay, next, we need to figure out, because we need to calculate the Ka of this, and in order to do that, because we know when this hydrolyzes, we need to find out what these concentrations are. So I need to find out, we of course know that this is X and this is X. We don't know how much product we formed, but I do know how much acetate I started with. Well, I know that I started with 0.005 moles, and I know that I have 50 plus 50, I have 100 milliliters. 100 milliliters would be 0.1 liters. So let's figure out what this concentration is. 0.005 divided by 0.1 is 0.05 molar for my acetate. So my acetate, 0.05 molar. All right, now we need to look at the Ka for acetic acid. We look on our Appendix D, and we see that the Ka is 1.8 times 10 to the negative fifth. But this has got to be a Kb expression because we're producing hydroxide. So actually what I'm going to write, you know what? To find Ka, we want to find Kb, right? Because we're producing hydroxide. When we have our products over reactants, we are finding hydroxide. So Kb, and since acetic acid is a Ka, we can find the Kb if I take my ion constant of water, 1 times 10 to the negative 14th, and divide it by acetic acid's Ka, which is 1.8 times 10 to the negative 5. That'll give me my Kb. So my Kb is equal to this. And then we have our products. X times x is x squared over reactants, 0.05 molar. And let's see what we get for x. X, which is my hydroxide concentration, right? So we're going to do 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. That gives me my Kb. Kb is, so then times it by 0.05, and then take the square root of our answer to get a hydroxide ion concentration of 5.27 times 10 to the negative 6. Okay, how do we find the pH if we know the hydroxide ion concentration? Well, if I take the negative log of this number, that gives me the pOH, and then 14 minus that answer, so 14 minus the negative log of OH should give me my pH, right? If I take the negative log of hydroxide, I get the pOH. 14 minus pOH will give me the pH. So let's just take that all together. 14 minus the negative log of my answer. And I get 8.72 for my pH. And if I think about that, we know that I have a weak acid and a strong base. So my equivalence point, we know that my weak acid, strong base equal amounts, but one of my products is acetate, and when acetate hydrolyzes, we end up with more hydroxide. That means I gotta have a pH of greater than 7. Makes sense? All right, let's look at this next one. We want to calculate the pH at the equivalence point. Remember, the equivalence point is when I have no limiting reactant. So I have to have equal moles of my acid and my base so that I'm using up all of my reactants. So let's look and see what we have. We have benzoic acid, and similar to what we did above when we were told benzoic acid, I'm just going to write HA. That's signifying my acid. It's titrated with NaOH. And so we know my products are going to be water and the conjugate base of the acid. We're just going to say A minus. All right, so we're told that we have 40 milliliters. I'm just going to do this. 40 milliliters. And my benzoic acid is 0.025 molar. And then I'm told that I have 0.05 molar of NaOH. 0.05 molar. Okay, let's figure out how many moles I have of my acid. So to find moles of acid, I just need to do my volume times my concentration. So let's do 0.025 times 0.040 liters to get 0.001 moles. Again, we know that we have to have 0.001 moles of my NaOH because I don't want any limiting reactants here. That's how we're going to find the equivalence point. Oh, that's not capital N. This is moles. 0.001 moles. So let's we need to find the volume of NaOH that we need in order to have 0.001 moles of it. So volume is, again, you can use this handy dandy little, we know that molarity is moles over liters. So to find liters, we need to do moles divided by molarity. So 0.001 divided by 0.05 gives us 20 milliliters. Okay, that will come in handy here soon. Now, we know that we're going to minus 0.001 minus 0.001, so we have no reactants here. That means we're going to plus 0.001 moles of my base, my conjugate base, which would be benzoate. We also know that benzoate is going to hydrolyze, right? Because it's from a weak acid. So we've got our A minus plus H2O, and that's going to make our acid again, our benzoic acid, and hydroxide, right? One of my H's for my water is going to go back over here, give me my conjugate acid, and then I'm left with OH minus. So this is another where I'm calculating, we're going to have a more basic solution. So similar to the last one where I go, well, I don't know what this concentration is, I don't know what that concentration is, but we do know our A minus from over here. We had 0.001 moles. Now let's figure out this concentration though. I had 40 milliliters plus 20 milliliters, which is 60. So that would be 0.06 liters. So let's do our 0.001 divided by 0.06. We get a concentration of 0.017. All right. 0.01, we'll go 0.0167. We'll go a little bit further. So we're going to say our concentration for A minus is 0.0167 molar. So that's our concentration for A minus 0.0167 molar. So now when we find our Kb, again for the acid, and way up above here, benzoic acid gave us the Ka, let's see here. No, where's benzoic acid? Right here. Benzoic acid is 6.3 times 10 to the negative 5. That's its Ka. So let's find the Kb by doing water, 1 times 10 to the negative 14, divided by the benzoic acid Ka, 6.3 times 10 to the negative 5. Again, this is my Kw divided by Ka to give us our Kb. And then that's going to be equal to x times x is x squared over 0.0167. All right, let's do some math here. 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 5. That gives me my Kb. So that times 0.0167 is equal to x squared. Let's square root my answer. And I get a OH concentration of 1.628 times 10 to the negative 6. So to find my pH from here, if I do the negative log of this, I get the POH. 14 minus the POH will give me the pH. So let's just type it in, 14 minus the negative log of my answer. I get a pH of 8.21 units. Again, it's going to be a basic unit because when I have my acid plus a base and they're in equal amounts and it produces the conjugate base from a salt is going to hydrolyze. When it hydrolyzes, it's going to form an equilibrium, which means a Ka constant or Kb constant. And this base is going to form a conjugate acid and hydroxide. That's how we know we're going to have a basic solution, because of what's being formed when it hydrolyzes. So we need the Kb is equal to x squared over the concentration that we found from the conjugate base. All right, we've got one more to do. All right, the last one, we're finding the equivalence point when we have 40 milliliters of 0.1 ammonia. So we have NH3 reacting with HCl. And we know that when we have NH3 base plus our acids are proton donors, so we will create NH4 plus, and our chloride ion. And we're told that we have 40 milliliters of 0.1 molar of ammonia. 40 milliliters, 0.1 molar. And we have 0.1 molar HCl. All right, so let's figure out how many moles of ammonia we have. So we've got 0.04 times 0.1 to have 0.004 moles. Again, we know the equivalence point, we need to have equal moles of our base and our acid, so we would have 0.004 moles of our HCl. And because we have same concentration, we will also have 40 milliliters of it. All right, so when we lose our reactants, minus 0.004, we have no limiting reactant. They're both completely consumed equally. We also know that we are going to form acid here. So we are plus 0.004 moles. And we know that that's 0.004 moles of 40 plus 40, 80 milliliters, or 0.08 liters. So 0.004 divided by 0.08 liters, so we have a concentration of 0.05 molar. Concentration there. And we know that our product is going to undergo hydrolysis. We know that our NH4 plus, which is our salt that is going to hydrolyze, so NH4 going through hydrolysis, forming an equilibrium to make NH3 and H3O plus. I'm going to erase this from my last one. Give me a little bit more room. Right, this is my NH3 and H3O plus. So we can see that I am forming extra hydronium, my H plus, my H3O plus. So I'm going to have a more acidic solution at my equivalence point. Now we've just found out that my concentration for NH4 was 0.05 molar. I don't know what ammonia is. I don't know what my hydronium is. So we're just going to form our Ka or Kb expression. In this case, we want Ka expression because we're finding hydronium ion concentration. But we know that ammonia is a base. So we need to take our Kw and divide it by the Kb to get the Ka. So 1 times 10 to the negative 14 divided by ammonia's, we look that up, should be 1.8 times 10 to the negative 5, which is my appendix D. Ammonia is 1.8 times 10 to the negative 5. And that's going to be equal to x squared over 0.05. 1 times 10 to the negative 14th, 1 times 10 to the negative 14th divided by my Kb, 1.8 times 10 to the negative 5th, gives me my Ka. Ka times 0.05. And then let's take the square root of it to get x. X is my concentration for H+, so it's equal to 5.27 times 10 to the negative 6. Let's take the negative log of that for my pH. Negative log of my answer to get a pH of 5.28. pH units. And again, this makes sense because after hydrolysis, after I've completely used up both of my reactants, both of my acid and my base, we know that acid is being produced. We found the concentration of that acid. It underwent hydrolysis, produced more acid. Therefore, we've got a lower than 7 pH.